Have you ever put on a VR headset and just forgotten where you are for a second? It feels like some kind of magic, right? Well, it's not magic, but it is an incredible mix of physics, computer science, and a little bit of psychology. Today, we're going to pull back the curtain and go under the hood to see how these virtual worlds are built to trick our senses so convincingly. So, to really get a grip on this, we're going to break it all down into four main concepts, or what we'll call pillars. These are the absolute foundations for any virtual world that feels believable. We'll start with making things feel solid. Then we'll get into how objects get a brain of their own. After that, we'll see the clever tricks that make it all run without crashing. And finally, we'll talk about the most crucial part, making sure it all actually works for you, the human user. All right, let's jump right into our first pillar. This is all about closing that gap between what your eyes see and what your body expects to feel. This is where the virtual world starts to feel tangible. So what is physical modeling? Well, it's not just about making a virtual object look like a brick. It's about making it act like a brick. If you push it, it should resist. If you drop it, it should fall. This is the science that simulates everything from how heavy something feels to how bouncy it is. And you might wonder, how does VR stop you from just walking through a wall? It's actually a really elegant four-step process. First, every single object, including you, gets an invisible force field around it, a bounding box. The VR system is checking, hundreds of times a second, are any of these boxes touching? The second they overlap, bam, a collision is triggered. Your movement stops, and your controller probably buzzes to give you that little bit of feedback that says, oops, you just hit something solid. Okay, so what happens when you do collide with something? Well, some things change shape. This table shows the two main ways that can happen. You've got elastic deformation. Think of squeezing a virtual rubber ball. It squishes, but it bounces right back to its original shape. Then you have plastic deformation, which is permanent. Imagine poking your finger into a piece of virtual clay. That dent is going to stay there. This distinction is what makes a world feel responsive and not just like a bunch of rigid, lifeless props. And here's where it gets really cool, how VR turns that collision into something you can actually feel. This is haptics. When your virtual hand pushes against a wall, the system calculates a force based on how far your hand has penetrated it. Then it smooths out that data so it doesn't feel jerky, figures out what your controller or glove can actually do, and then, boom, the device pushes back or vibrates, creating that physical sensation of a solid surface. So, to wrap up our first pillar, physical modeling is way more than just lines of code. It's the reason you'll instinctively jump back from a virtual baseball flying at your head. It's what gives the virtual world a sense of genuine substance. Okay, so now our objects feel solid. That's a great start. But a bunch of solid objects just sitting there isn't a world. It's a digital statue garden. To bring it to life, things need to do stuff. That brings us to our second pillar. How do we make virtual objects actually act real? And the answer is behavior modeling. This is where we give the objects a brain, so to speak. It's the set of rules that decides what happens after you interact with something. Physical modeling makes you feel the ball when you touch it. Behavior modeling is what makes that ball roll away. So how does this brain work? It's actually built on some pretty simple ideas. First, every object has a set of states it can be in. A door, for example, is either open or closed. Simple. Your actions, like grabbing the handle, are the events that trigger a change from one state to another. And the whole thing is governed by basic if-then logic. If you press the button, then the door opens. It's the fundamental cause and effect language of the virtual world. And that simple logic can create all sorts of different movements. You can have a predefined animation that's perfect for something predictable, like a door swinging perfectly on its hinges every single time. Or you can have physics-based motion, which uses the rules we just talked about to create something natural and unpredictable, like a ball bouncing around a room. And then you have the really advanced stuff, AI-controlled movement, where a character can actually navigate the world and make its own decisions. So the big takeaway for pillar number 2 is this. Behavior modeling is what breathes life into the world. It's the difference between a static diorama and a living, breathing environment that actually reacts to what you do. Okay, so we've got a world that feels real and acts real, but a truly immersive world can have millions of objects in it. So how in the world do you render all of that at once without your headset grinding to a halt? The answer is our third pillar. Model management. This is all about working smart, not just hard. It's basically a whole toolbox of clever tricks to make sure the system is only rendering what you absolutely need to see right at that very moment. And why is this so important? Because of this number, 90 frames per second. Anything less than that, and you start to get lag, stutter, and that horrible feeling of motion sickness. So model management isn't just a nice-to-have feature, it's absolutely essential to make VR comfortable and immersive. One of the cleverest tricks in that toolbox is called level of detail, or LOD. This system is incredibly smart about this. It knows that a building way off on the horizon doesn't need to have every single brick and window rendered perfectly. As you can see here, the farther away something is, the simpler the model gets, all the way down to just a basic gray box. This saves a massive amount of processing power, which can then be used for the stuff that's right up in your face. So, the big idea for this pillar is that a believable world has to be a smooth one. Model management is the unsung hero working behind the scenes, making sure that the beautiful illusion of reality is never shattered by a lag spike. And that brings us to our final pillar, which might just be the most important one of all. You. How do designers make sure that a world that works perfectly on paper is actually intuitive, comfortable, and, fun for a real person to be in? Well, that's the science of human factors. This is all about looking past the code and the graphics to study the actual human experience. Is the system easy to use? Is it confusing? Does it feel natural or clunky? This is where the technology has to meet psychology. Now, to figure this all out, researchers collect two types of data. You've got your quantitative data. These are the hard numbers. How long did it take to finish the task? How many mistakes did the user make? But numbers don't tell the full story. You also need qualitative data to understand how it felt. Was the user frustrated, confused, delighted? You need both the what and the why to really understand the experience. And this is how all that data gets put to use. It's not a one-time thing. It's a constant cycle of improvement. Designers build something, they test it with real people, they see what works and what doesn't, and then they go back and make it better based on that feedback. This loop, test, improve, test again, is what turns a clunky tech demo into a seamless, intuitive experience. So the key takeaway here is that a great VR experience isn't just built, it's discovered. It's found through this relentless cycle of testing, listening, and focusing on the human who is at the very center of all this technology. And there you have it. Those are the 4 pillars holding up every believable virtual world we experience. You need physical modeling to make it feel solid, behavior modeling to make it act intelligently, model management to make sure it all runs smoothly, and human factors to make sure it's an experience worth having in the first place. Which leaves us with a final question to chew on. We've gotten incredibly good at simulating sight and sound, and we're making huge strides with touch. But as these worlds get closer and closer to our own reality, it makes you wonder, what's the next great challenge? What human sense will be the final, most difficult frontier to conquer in the virtual realm? Something to think about.